Good morning, everyone. That should have been enough time for everyone to filter in. We've got a couple of latecomers, but I think we're going to get started. Welcome to our webinar of your guide to HV cable testing, both online and offline testing. I'm Thomas Whyte, one of the senior engineers at EA Technology, and with me is Brad Monaghan, who's the head of services in EA Technology Australia.
Hello, everybody.
We've got a lot of content to get through today, so we're going to crack on quite quickly. If you do have any questions, there is the Q&A box as part of this. We are going to try to get through all of the questions, but we've got a lot of content, so please bear with us. If we don't have time to get through to questions today, we will try and catch up with you afterwards in order to make sure everything is answered. A bit of a highlight about this. This is part of a two-part series of webinars. So today we're looking at guides to online and offline testing, and we're going to touch a little bit on a bit of network analytics and small things. But in our next webinar, which is coming up in August, we're going to really look at how we take all of the test data we're talking about today and integrate that into your asset management regimes, as well as your asset management strategies for maintenance. So I'm going to talk about that a bit later on. Today, what we're going to run through is a bit about offline and a bit about online cables. Brad's going to take you through all the offline cable testing, what's possible, what you're looking for, and what you should be doing. Then I'm going to come in and talk about the online side of testing, what the differences is, how you want to target your different assets, and then talk a little bit about the network analytics. But most of that will be saved for our next webinar. So once we start to think about the testing of HV cables and why we're doing it, the main reason is improving asset performance and increasing safety of our networks. And we do these tests either during commissioning or during part of a regular condition monitoring program. But the main goal is giving us enough data that we can move from reactive maintenance into a more of an active maintenance program. And we're going to talk about a lot of what we do and what steps you take in order to reach that process. So when you think about HV cables and when you think about all your testings, you need to know what are the failure modes of your cables. That's the most important part when you're thinking about all of your testing methodologies. So there's been some great studies done on HV cables and failure modes, and this is one that came out of America. They looked at a large sample of HV cable failures, and what they found was 57% of HV cable failures could be related back to workmanship as the root cause. And that is a huge population. Manufacturing defects weren't insignificant, they hit 16%. But one of the really important things to note is only 9% of those defects were in the cable run itself. The other 7% were in cable accessories such as terminations or joints. So if you think about that data in relation to what we're actively trying to find and the problems we're trying to remove off your network, you're trying to look and investigate places on HV cables where humans and workmanship defects become more prevalent. And the reality is, that is your cable terminations and your cable joints. So a lot of the testing we do is actually focused on identifying problems in those areas. It is important to note that in this data set, age-related failures weren't the most significant cause, but that will actively change as networks age. So as we do tend to progress into future networks and as all of our assets get older, we may see an increase in age-related failures. But if we're doing all the right testing as we approach that, then we should be able to throttle that back down and maintain the network reliability. So I'll pass over to Brad, who will run through all of the offline testing options.
All right, so let's talk about some offline cable testing. So we're going to mainly focus here on IEEE 400.2, which was published 2013. That was the last time that standard came out, which focuses on VLF testing from 5 kV up to 69 kV. We'll talk about some other tests that aren't VLF tests, but that's what we're focusing on. I'm not going to talk about factory acceptance testing, but it's mainly distribution cables that are already in the ground or have just been built. Okay, So what tests are possible and what's normal and what are extra tests that you can do in the future? So if we start looking at the standard, the first test that you'll generally run is an acceptance test. And the standard says that's a field test made after the cable system installation, including the terminations and the joints, but before it's been placed in normal service. And that's when you run those tests. So once you've built it, you've joined it, you've terminated it, it's ready to go in service. What do you do? So what's generally normal is that you will do all your pre-withstand tests, which you'll do a sheath test, you'll do a continuity test, you'll do a phasing test. You can do sheath continuity, you can do conductor resistance from end to end as well. But generally the sheath test, continuity and phasing are the main ones that happen. And then what you'll do is you'll move on to your withstand test. So what that generally involves is a pre-insulation resistance test, then your VLF test, then your post-insulation resistance test. Then you'll turn that cable on and you'll load it up as long as it passes all those tests. And then sometimes if networks allow and that the rules within those networks allow it, what you can do is just an insulation resistance test on its own. You'll do no VLF tests and then you'll remotely switch that cable on. Remotely switch means you'll go to the next high voltage switch back from where that one gets loaded up from and close that switch. Or you can do it remotely via a gas switch from the control room or whoever it may be, and you will turn that cable on. You'll then soak that cable for X amount of time, so maybe 1 hour, 24 hours, depending on what your rules are, and then you'll load the cable up, and then it's fully placed into service. So it's generally company specific, but they are very normal things to do. And then what some companies will also do, and what we recommend doing, is some condition monitoring tests at the start when you build your actual cable. So then you've got some data to trend over time and you'll pick up some lower level defects or defects that you've built in or defects that the VLF test itself has brought on, potentially when the test was running. So those three tests mainly are is the tan delta test, the PD test, and then there's also a LIRA test. So it's important to note here that the basic commissioning tests at the start are generally not trendable, and the ones down the bottom are definitely trendable. So it's good to get that benchmark. And we're going to focus on these things. So the next slide. So then what you've got is maintenance tests. So after you've built the cable, commissioned it, done your acceptance testing, that's the first type of test. And then after that is a maintenance test. The standard calls that to be a field test made during the operating life of a cable system. So after it's been turned on, as I said. Generally, this test, or these tests, these sweeps of tests, are conducted under 3 different situations. So whenever you make a modification to that cable circuit, so just say you want to cut in a new substation because a new building got built, you want to make that cable longer, cable shorter, whatever you may be doing to it, you need to run the suite of tests again to see if it's safe to turn on again. Repairing after a fault. So if your cable blows up, you'll generally cut out the faulted section, put in 2 new joints or pull in a new section of cable and do 1 joint, whatever the repair may be. You'll want to do that again. And then the third one is part of a condition monitoring program where you will actively turn the cable off, not make any changes to the cable itself, any physical changes, and then you'll run a suite of condition monitoring tests on that. So for the condition monitoring program, the focus then shifts from a pass-fail test of what those normal initial tests are to spotting some emerging trends and seeing if things are getting worse over time. That's when you're doing that, it's ideal to have that benchmark condition monitoring test, what you did at the very start, to assess for insulation degradation over time. You've got a baseline to compare it to and see how your insulation's performing. Okay, so what defects are possible? When we're talking about defects, we want to know what defects can be in a cable, and then we want to know where the defects are. So where the defects are is another, continue. We're all good. Where the defects are is the most important thing. Okay, so in extruded cable system, defects are, for an example, this is taken from that standard, you've got interface problems, protrusions, connectors, moisture penetration, water trees, contaminants, cavities, delaminations of the shield, conductor problems, faulty material, etc., etc. You've also got a lot of those things there can be caused by installation and workmanship defects, within the joints. The terminations also when the cable gets pulled into a certain extent. But as Thomas said before, the most common parts are workmanship defects in the joints and the terminations. Now, it's important to note here that these defects may be revealed during your withstand test. Your withstand test is that VLF test that you run at the start. If your VLF test is going to bring out a fault, that tends to bring out a major fault with the cable. An electrical tree starts to happen, so it starts to burn and arc from the inside of your insulation. And then as your VLF test set runs for for more time, that tree begins to get bigger and bigger and bigger, and it'll run away to failure during your test. Hopefully, it runs away to failure during your test. That's why we run our tests for certain amounts of time. But also keep in mind that electrical trees may have been initiated, but it didn't fail during the test. And that's where a condition monitoring test will find that type of defect before it fails. We've got pictures here. The one on the left there is an electrical tree that's formed, and the picture in the middle and the picture on the right are some water trees, examples from some literature. So first, let's get into withstand testing. Withstand testing is basically your VLF test before you turn on. Or it's called a whole bunch of things. It's called a HIghPot test. HIghPot is short for high potential test. It can be called a pressure test. It can be called a VLF test. It can be called a withstand test. It can be called an acceptance test. Whatever your lingo is, it's all the same. It all means the same thing. So the commonly accepted standard for that, again, is that same standard, 400.2-2013, VLF testing of shielded power cables at less than 1 Hertz. So with a VLF test, VLF stands for very low frequency. There are 2 main wave shapes that will generally get created by your test sets. Whoever makes that test set and whatever the test set is capable of, it's very common to have 2 types of wave shapes that come out of it. The first one is sinusoidal, which replicates the AC sine wave that is on our 50 or 60 hertz network generally because of the way we've created our electrical systems since electricity was invented. AC anyway, I should say. And then you've got cosine rectangular. And those 2 shapes are shown here where my mouse is on the bottom right-hand side. The sinusoidal wave shape is the most common one used. And then VLF can be performed at from 0.01 Hertz up to 1 Hertz. So that fits the standard of what VLF is called, where 0.1 Hertz is the most commonly accepted frequency used. So 0.1 Hertz equates to 1 cycle every 10 seconds. So it'll go from its 0 up to its positive peak, back through its 0, down to its negative peak, and then all the way to its 0 crossing again every 10 seconds when it's powered up by a 50 Hertz power point or generator or whatever you're using to create that. Be a bit slower for your 60 Hertz. Ideally, testing would be performed at 50 or 60 Hertz on the cables, but to do that you do need large transformers because you need to be able to power up the capacitance of the cable. Those transformers are generally expensive and inaccessible, so that's why VLF testing was invented. So if we do it at 0.1 Hertz, we're only using 1/500th of the power required to run that test. So it sort of means that the test set can be 1/500th the size of it. I don't know if that actually works, but your test sets are generally quite small. They're quite light. They'll fit in the back of your car. They can be moved around site easily. That's why we don't use huge transformers. And then DC testing. We could use DC testing. They used to use DC testing for paper lead cables in the past. Those test sets would generally be about the same size as your VLF test sets are now, or a bit bigger. But they don't use them anymore on XLPE cables or paper plastic cables because it was proven a long time ago to be able to damage those cables, also not reveal issues that AC can. So that's what VLF is. So is a VLF withstand test, is it diagnostic? So that's up for debate, but generally it's not. It's generally a go or no-go test. What you're doing with that test is you're putting on a certain voltage for a certain amount of time and seeing if your cable blows up during the test. So the questions come along. If you held you finish your test and it doesn't blow up. So the questions come about if you held those volts on longer, would the cable have blown up? Maybe, maybe not. Has the test caused electrical trees within the cable that are going to blow up in, you know, the coming days, months, weeks, years, or were there defects there that the VLF didn't bring out and there were electrical trees? Electrical trees is partial discharge, it's sparking and arcing going on inside the cable. Would that have been brought out? Many variables that affect the times of failure in cables. So you've got the cable type, so what it's made of is the paper, plastic, different types of plastic, the geometry of the defect itself, the location of the electrical tree, the test voltage applied, and the frequency. So all of those things will have a different variable as to how long something takes before it blows up. When we run a VLF test, generally the most diagnostic thing you have to look at when you're running that test, when you're looking at the front screen of your VLF tester, is the milliamps that it's taking to run the test. So what you generally see on the screen is you'll see where your sine wave's at, you'll see how much power or how much voltage you're putting on, but then you're able to measure how much power it's taking to run the test. So if you stare at that milliamp reading and that changes over time, that could mean that you know, something has occurred and something has changed. Or it could mean that the cable's just dried out a little bit, or the terminations have dried out a little bit and it's taking a little bit less power to run that test. That milliamp amplitude has no pass or fail. It's just how much power did it take to run this test. So if damage did occur when you run your VLF test, would your post-IR test reveal it? So would your post-IR, when you do that insulation resistance test after your VLF, will it reveal that there's a defect there? Keeping in mind that most of your post-IR tests are only at 5 kV. So would 5 kV be enough stress to be able to see if you've made a change when you might be high plotting your cable at, say, I don't know, 25 kV? Also, will the milliamps change? They're all the questions about have you done any more damage. If damage is occurring to the cable during the test, there may be no indication to the user that damage has occurred. Okay, so VLF testing, what voltage and for how long? So every company tends to come up with their own test procedure or recommended test procedure for themselves. But when we look at the standards, the VLF standard is generally between 2 and 3 times U0. U0 is an accepted way of saying your RMS phase to volts of whatever you're going to liven up on that system. So for a 33 kV system, that's about 19 kV. So that's generally the voltage level you'll go to for commissioning. And then once you've commissioned the cable, you generally don't go to that voltage again. So you stress it when it's first built, and then every time you high plot the cable after that, you'll generally only go to about 75% of that voltage level for maintenance tests. And then how long do you test the cables for? So when we look at the standard, it suggests 30 minutes for old cables, 60 minutes for brand new cables, and 60 minutes for important old cables. And then what they've got in there is what's called monitored withstand testing. So that's when you're doing your withstand test with VLF, you can also monitor PD and tand alpha at the same time. And if you're doing that and there's no problems occurring, you can drop the length of the cable test down to 15 or 30 minutes. And there's some writing from the standard there. Single phase to earth testing is the most accurate. A lot of companies will hook all 3 phases together and just liven them all up at the same time. Keep in mind when you do that, if you've got portions of your cable where it's not individually screened around the cable, you can have a phase-to-phase fault that you're not detecting. So that's why they say single phase. So just say you liven up your red, your earth, white and blue, run your VLF test. That's going to be your most accurate and meet the standard, the best way to bring out the most amount of faults. So that's what you're trying to do. Here's a table about all the voltage levels. What is generally accepted is the sinusoidal waveform. Here on the left-hand side are the voltage levels that your cables are going to run at. What I also look at here is none of these actually meet any Australian ones, not that that matters, but Australia has 33 kV, 22 kV, 11 kV and 6.6, but none of them are written here. So I suspect a lot of these have come from just other voltage levels from around the world. And then on the right-hand side here, we have acceptance tests and maintenance tests and the recommended RMS voltages to go to. They do have your peak voltages in there, but you can just do some maths and figure out the difference between the two. There's another set of values in here called installation testing. What installation testing is where you go out in the field, run your cable, don't terminate it, and don't put any joints in it, and you high pot it before you join anything. I've never personally done that test, and I would say that that's not generally done in my experience or our experience, but it is there, and it must be done at certain spots around the world. Just going through the standard with you all. All right, so let's talk about condition monitoring testing. So types and when to use. So as I said before, withstand testing alone may not reveal all issues. It's probably going to bring out your high level issues, but there can be some low level issues there that are waiting to fail in, days, weeks, months, years after you commission your cable. So during commissioning, we can gain a benchmark, identify low level problems that didn't fail through your withstand test. In your maintenance test, you can trend known issues over time. You can also identify problems that have arisen over time since your benchmark, if you already did a benchmark one, and then after a cable fault. So if you're cable faults, you can detect further issues in that cable if they occur during the fault. Types of testing can include your tan delta, PD, and your LIRA testing, which are the ones that we're going to talk about now. Okay, so let's get into tan delta testing. Tan delta testing. So what does tan delta testing find? Tan delta testing is mainly designed to find water ingress into cables, especially your XLPE cables. So in XLPE, water can get in there and cause cancerous-like growths in the form of many thousands of little water trees, and these water trees get bigger and bigger over time. It does take a long time for them to get bigger and worse over time, but what can eventually happen is the water tree gets bigger and longer, and it bridges out a fair portion of your insulation. And then once it's bridged that out, an electrical tree can start to form, which is partial discharge, and that very quickly can run away to failure because it's just bridged out the last portion of your insulation between phase and earth and blow up your asset, blow up your cable. So that's what it says here. Water trees lead to electrical trees, which can lead to failure. And that can run away in a short amount of time. So what you want to do is figure out if you've got water trees in your cable, because the chance of finding the PD at the end of those water trees is quite low, because all the research suggests that it's going to run away very fast and blow up. The defect, also what tan delta can find is any defect that's going to cause leakage current through the insulation or on the outside of the insulation. So that's through the insulation is your water trees, but also if you've got dirty terminations, wet terminations, it's going to have leakage current on the outside of those terminations. So when you do a tan delta test, if you get a bad result and you suspect there's no water trees in there at all, what else could it be? What's going to give me some leakage current that shouldn't be there effectively? So that's the thought process of the tester or the people that's analysing the test results after the fact. How does it work? HV cables with their insulation are a near perfect capacitor, because a capacitor is two conductors separated by an insulation. So if it was in a perfect world, the phase angle between your volts and your current is going to be 90 degrees. And we don't live in a perfect world. We live in cables, it's slightly less than a perfect world. So there always is a tiny bit of resistive path there, but the bulk of it is a capacitive path. It's a capacitive current. So effectively the phase angle between the two is very close to 90 degrees. I'm just trying to turn my hands there so you can see a 90 between my hands. As impurities, water trees, electrical trees, air pockets, etc., any type of defect is introduced, there's more of a resistive path between the conductor and the earth through your insulation. So that's going to reduce your phase angle between your volts and your current. So as that comes in, your phase angle gets away from 90, which will increase your tan delta level. And that's when you can pick up that there are problems. Okay, so the pros of tan delta testing is it's relatively quick. What you do is, to meet the standard, is what you'll do on each phase. So on your red phase, your white phase, your blue phase, you want to collect 6 data samples at each one. So you want to let 6 cycles of electricity run through it. So it's 60 seconds really, at 3 to 4 different voltage levels. Generally what's accepted is you want to run your first one at 0.5 times U naught, 1 times U naught, 1.5 times U naught, and then 2 or at your highest test voltage level. So you'll end up with 3 or 4 data points along a graph, and you'll be able to see what the tan delta was at half your volts, your system volts, 1.5 times your system volts, and then 2 or higher. Also, another good thing is if you find a tip up in your lower voltage levels, if you see the tan delta going, extremely high or changing where it shouldn't be changing, where you wouldn't be expected to change, you can stop that test and then think about, right, what's going on here? Why have we got that? To prevent more damage going on by increasing your volts, because to finish the test, you've got to turn the volts right up. So some of the cons about it are it's a bulk measurement. Tan delta testing won't localize a defect to you. You'll run one test, you'll get one answer at that voltage level, at that one cycle. But it's not going to give you, it's not going to say, right, 152 meters down the cable, you've got a water tree. It won't say that. It'll say your cable from end to end is this level of tan delta. There may only be one, because of that, there may only be one section of cable that's bad that brings down the whole reading. And mixed cables may not show bad XLPE sections. And what that means is, just say you've got a new XLPE cable of 20 meters that's been cut into a 500 meter run of paper lead, which is pretty common around the place. You do a tan delta test on that. If you get a high tan delta test, you don't know if that's caused by the XLPE, which should be really low. Paper lead generally has a higher tan delta level, or its levels of its allowable limits are higher. So that can make things a little bit tricky, but if you run the test and have a good think, you get what you get. Okay, so that standard has recommended limits. That's on the next slide for you. In general, an increase in the tan delta reading compared to the previous one and compared to your data set of similar cables and all that indicates that degradation has occurred. If you'd run the test, X amount of years between each other and the tan delta reading is going up, degradation is generally occurring. To assess I won't exactly go into how to assess it, but generally what you'll do is you'll have 6 data points at 4 different voltage levels on 3 different phases. And what you do to assess that data is you look at the voltage at each, or the tan delta reading at each voltage step, the change within the 6, the comparison of the phases between each other, and you want to assess the overall amplitude of them all. So when we look at the patterns between those, because you can obviously plot a few graphs from all those data points. When we look at that, you can draw some pretty good some assumptions, such as water trees are in the cable, moisture is ingressing into the cable as the test is running, water is vaporizing out of the cable as the test is running. You can see wet joints, and also you can see PD. So if you've got PD there and sparks are occurring, it takes a certain amount of power to run those sparks, and that is leakage current, and that can get picked up by your tan delta, or probably will get picked up by your tan delta. So it can also give you an indication that PD is occurring. But the best way to figure out if you've got PD occurring is to run a PD test, obviously. Okay, so here are 2 different tables. There's a few more tables within the standard, but paper lead cables and plastic cables, you can see that paper lead has higher allowable limits, plastic cables have lower allowable limits. Then let's do partial discharge. All right, so partial discharge is a VLF test. I probably didn't say it before. The tan delta is a VLF test, obviously, because you need to go to those voltage levels. PD testing is also a VLF test. You need your voltage supply to supply the power. You hook up a coupling capacitor and a voltage divider and some smart electronics and some smart hardware and software, and you basically measure the PD pulses occurring, if they are occurring in the cable or anywhere in whatever you've just livened up. It will come back to your test set. You can measure it. You can figure out where it is. You can count them up as the test goes, and all of those types of things. So you can run the PD tests during your whole withstand test. So you can measure to see if any PDs are occurring. You can do it no matter what the voltage level you're applying, as long as your test set can take it. You can also ramp the volts up. You can ramp the volts down. If PD does occur, you can measure what's called the PD IV, or the PD inception voltage. And what that means is there'll be a certain voltage level where PD starts to happen. So just say you've got a 10 kV cable, and at 7 kV PD starts, and then it probably gets worse and worse and worse as your volts go up. And then what you'll do is you bring your volts back down, and it might not stop until about 5 or 4 kV. And what that's called is your extinction voltage, PD extinction voltage. Because you have control of your volts with your VLF set, you can measure those two things. And those two things are an important piece of information as to, was there PD on the cable? And what I mean by that is, if you have a 10 kV cable and PD doesn't start till you put 15 kV on it, there's a good chance that PD is not going to be happening on that cable in normal service. It's just that there is some sort of defect there that's going to kick up if your volts get up to 15 kV, or if something tips it over the edge. So if you get a lightning strike in the area, some sort of transient runs through your system, it can kick off PD because it instantaneously got 15 kV on it, for example. Some of the softwares will give you phase resolved partial discharge patterns, which you can analyse and show what type of PD you've got, or if you're measuring some sort of noise. There's a couple of different standards that are written there. They're not all the standards, but if you want to look them up, go for it. And there's some good readings to be had. This is basically the way that it happens in a real life situation. So you'll have PD occur. It'll spark at some point along the cable route. A electromagnetic pulse will travel away from itself and travel both ways up the cables, and that effectively goes up and down the cable, and they cross over each other and they bounce off the ends of the cables. We've got our test equipment set up at one end of the cable. We're able to measure those pulses and get some sort of distance to it. So this is what it looks like in real life. You'll have your PD pulse that occurs, your reflected pulse, and then another reflected pulse, which is actually the first one, which bounces off the end of the cable. So the way we quantify partial discharge when we're doing offline testing like this is it'll be measured in picocoulombs or nanocoulombs if it's very high. To come up with that answer, what they do is, what the software will do is it will measure the area underneath the initial pulse, and that's your picocoulomb level. Okay, and then what we can do is use time domain reflectometry to measure the distance between the pulses. That'll give us a pulse from the near end to the far end of the cable, and the near end to where the PD is occurring. So you can say, hey, on this 700 metre cable, you've got PD at 540 metres down the cable. Let's start thinking about what we can do about that. Okay, so as I said, picocoulombs, nanocoulombs, that's what they get measured in. Picocoulombs are less than nanocoulombs. To run the test, before you put your volts on, you'll hook everything up. Then you'll put a calibrated pulse into the circuit. Change the calibration level of that pulse, see that your software is seeing it. Generally at that point, you'll be able to see the far end of the cable, measure the distance, set up your speeds, and set up all your distances, and then take that away once it's all calibrated, and then you put your volts on. Once you put your volts on, you just basically wait and see if any PD occurs. If PD is occurring, you measure it, you try and get a distance to it, you try and see what its inception voltage is, its extinction voltage is, and that's the point of the test. Ideally, there is no PD, and you may be able to shorten the length of that test because you've done what's called a monitor withstand test. Okay, here's some allowable limits. You'll see that XLPE has lower allowable limits than paper lead cable. That's because XLPE is rubbery and it tends to burn through quicker when sparks are in it, as opposed to paper lead cables. Paper lead cables have paper, it has oil in the paper, and it can take more burning than a plastic cable can. So that's based on years of experience from EA Technology doing VLF tests, mainly in the UK, to come up with those. Okay, and then let's get into LIRA testing. So LIRA testing, this is what the LIRA tester looks like. You can see it on the left-hand side here. So it's very small, very portable. You just, it's not a high voltage test, but you do need access to the HV. So you need to get either an access permit or a sanction for test, whatever you guys need to give. It will put on somewhere around about the 10 volts. So it's a very low voltage test. And you just go between phase and earth or phase to phase, and you basically inject a whole bunch of different frequencies, oscillating frequencies that will run through the cable at a very low level of voltage, as I said, 10 volts. And then we measure the pulses that come back, and we measure all the information that comes back. So how does it work? It's called LIRA, line impedance resonance analysis. It can detect and measure distance to local degradations or faults. It can also do global degradation, like a tan delta test, where it's the bulk of the cable. So it's very sensitive to small changes in the insulation material. It calculates the impedance spectrum as a function of the applied signals over a wide spectral frequency. So what it's doing is it's looking for bounces reflections in the impedance when you apply different types of spectrums of that 10 volts that you put on them. It also has TDR functionality, so you can get a distance to problems. Why to use it? So what you can do to use it is you can gain a benchmark and then compare that in the future. You can perform fault locations with it, because if you've got an open circuit somewhere or a short circuit somewhere, it's going to look different to the other two phases. So we will see a change in impedance at that location. You can identify distances to joints. Some TDR testers are powerful enough to do that, but this one here, you can tell it to put on a whole different range of frequencies all the way up to, I forget what it is, but hundreds of megahertz. And what you're able to do is analyze that data and pick up where their joints are. And you may not have known those joints were there to help with your cable records. It takes about 20 minutes to 30 minutes to run all the tests on all three phases. It depends on how many frequencies you're applying. It can test extremely long and very short cables. So it can test cables that are 15 meters long up to over 300 kilometer long cables. And so when you've got cables that are that long, this is one of the only tests that you can run, because you can't run a VLF test on a cable that's 300 kilometers long unless you've got a massive power transformer that's going to liven that up. It just won't be able to beat the capacitance of the cable. It can also test any voltage cable, anywhere from low voltage all the way up to 500 kV cables, a million volt cables, whatever it is. It doesn't care about that, because it just puts 10 volts on. It sees what impedances come back, reflections, and it's also powered by a laptop, so it's very portable. You can move it around pretty quickly. So what will it find? It'll find, as I said before, the global insulation degradations, high temperature damage, moisture damage, radiation damage, mechanical effects or defects, and it can also find PD sites. This is a trace here of a typical TDR trace with your red, white and blue all laid on top of each other. This was one where we didn't find any defects, but these were distances to joints along the cable run, and you can see the impedance changes coming back. So it is a useful piece of kit. It's also, we tend to use it, so we'll run our PD test, we'll run our tan delta tests, and then while we're packing that equipment up, we will run this test, because it's relatively short and you don't need any HV to do it. So you can go right up to the cables, make all your connections, break all your connections, and you don't need to be turning VLF sets off, earthing, safety-wise, all that type of thing. Okay, so a summary. So withstand tests are generally a pass-fail test. Is it going to blow up if I put this amount of volts on for this long? Is it safe to turn on once the test has passed? And then once it's passed, it's unknown if a low-level defect is still present, or if a low-level defect was caused by the test itself. Was it caused by the voltage that you applied? Condition monitoring tests will identify, measure, and can locate defects, which is ideal for what you're trying to do. So in general, the easiest way to think about tan delta is it's going to find water ingress or anything that's going to give you leakage current. So leakage on your terminations or through your insulation. That's how you need to think about what a tan delta test is going to do, and it's a bulk measurement. Okay. Generally, PD will find electrical trees. Electrical trees is PD. PD is sparks occurring within the insulation. So it can measure them. It can find when they happen on what voltage range. It finds when they go away, and it can localize them to where they are along your cable. In general, LIRA will localize impedance changes, whether those impedance changes are joints or defects, looking across a broad range of frequencies, which is a very handy thing to do. It can test very long, like extremely long cables, and very short cables as well. So it's a useful bit of kit. And all of them can, all the data can be saved from them for trendable over time. And that's why condition monitoring testing during your commissioning is optimal, because you've got that snapshot in time. A lot of cables are already in service, but it doesn't hurt to jump in there and do that as well, to start somewhere. Okay, so now I'll hand over to Tomo, who's going to go through our online cable tests.
I see that.
Yep.
There's just a bit of a delay in the questions, so
cool.
They're still coming through. So moving on to online testing, and the transition from offline testing to online testing has some great advantages and some difficulties. So we're going to run through a bit of everything. So When you move to online testing, there isn't as big of a range of the tests that you can actually run. Partial discharge testing is one of your primary options when it comes to online testing of HV cables. There are a lot of advantages to this, and the main ones being that they're completely non-intrusive to your network. It doesn't require any outages. It doesn't require you to take your cables offline in order to do the testing. They're also completely non-degrading. Brad talked about the issues with withstand testing and you not knowing if you have missed some small degradation or you have introduced some small degradation onto the HV cable. That isn't a risk with online testing because you're doing the testing when the network is operating and its normal operating conditions. It's also quite a short testing period, so it allows you to get in and out doing a large amount of testing in a short period of time. For Brad and I, if we're doing large fleets of cable testing jobs, we would traditionally allow 30 minutes to cable test an RMU, which is testing a cable in, a cable out, as well as performing full partial discharge testing on the RMU itself. So you can get through it very quickly compared to offline testing. Due to this, it's very inexpensive. You can do a lot more of online testing than you can offline testing for a lot smaller amount of money. And that's really critical when you're managing a quite large fleet of HV cables. Some of the things that are most important is online testing is capable of continuous monitoring. With offline testing, you aren't capable of leaving an offline test running for large periods of time and trending it. It's a snapshot. Whereas online testing, you can leave the sensors in situ and you can get live data, which allows you to make much more informed decisions. And that's a very powerful tool for asset managers because it allows you to see what is happening on your network in effectively real time. And whilst doing this, you do still have all the tools like location of defects and everything like that, and really good quality trending. Some of the disadvantages are that once you move to online testing, you begin to test a network, not just a single HV cable. And due to that, it does take a little bit more analysis, and it's also a little bit more susceptible to noise and interference, but that's all manageable and there are ways within the test to work around that. It relies on accurate cable records, and for the HFCT testing, which I'll talk about in a second, you do require access to your earth screens off your terminations. So Brad talked a lot about the standards for offline testing, and once we move online, they aren't as well defined. You do have two standards, which I've noted here, which are IEC 60270, which was published in 2000 with an amendment in 2015. And this is quite a good standard for going through the test techniques and methodologies, but it doesn't offer set thresholds and testing methodologies in the same way that offline testing does. There's also a secondary standard, which was published as a complementary document, and that's IEC 62478. And that expands online PV testing into the higher frequencies, but it isn't as relevant for HV cables. So when you start to do the testing with online partial discharge particularly, it is a bit more reliant on companies like EA providing people with guidelines and documents in order to manage their networks. So what is possible? And there's a number of different tests that are possible when you look at online partial discharge testing at HV cables. The simplest is ultrasonic testing, and ultrasonic testing is looking for surface type tracking, electrical training, but it is only really testing your terminations. Because as I talked about in the beginning of the webinar, the points where we're really looking to focus are on your terminations at either end and your joints along the cable span. So ultrasonic signals do not travel along HV cables. So when you're doing your ultrasonic testing, you are only really checking your terminations for surface tracking or when your HV tolerances are too close and you get an interaction between unscreened cable phases. You then have the option of doing TEV testing. TEV testing has a little bit more power in terms of testing the entire cable span, but I would say it still primarily focuses on the cable termination itself. TEV testing, the signals will begin to run along the length of the HV cable. So you will see some signals, if you've got a problem in a joint, coming up, and you will find them. The problem with TEV testing is you don't have the power and location that you do with the HFCT testing, which I'll talk about next. You're able to do some location where it will tell you if it's coming from the termination or further down the cable, but you're not capable of getting the exact distance. But you are looking for those internal void type defects, the issues within the insulation layers, which is what you primarily find within joints. HFCT testing is your primary test method when it comes to HV cable runs. And this is the test method where you attach a split core current transformer. It goes around the earth screens of your cable termination, and it detects the small current pulses which are bouncing up and down the cable because they're being emanated from the PD source in the cable joint, for examples. You do have the power to filter these signals in order to remove noise and get a cleaner signal, but more importantly, you have the ability to analyze the waveform, same as on the offline testing, where you can look at the relationship of the waveforms reaching you, and you can do some maths to figure out how far down the cable it's coming from. We work with a number of clients in cable testing. Some are quite lucky, and a lot of their earth screens are accessible during normal network operation. And that makes this test very quick and very easy. If you are a company and your earth screens aren't accessible, they're tucked away inside cable chambers, you do still have a number of options. We work with some clients who permanently install the sensors within the cable chambers. They then bring them to a breakout box, and you can just plug into the outside and it's perfectly fine. Others extend the earth screens themselves and bring them outside of the cable box so you have direct access. Both are very viable methods, but if you can do it and set yourself up to do this testing without interrupting network supply, you have a really good method of keeping an eye on your HV cables. The most powerful tool when it comes to the online testing is the fact that you can do widespread testing. And the widespread testing is really more realistic in online testing than it is in offline, due to the fact that offline testing requires an outage and it requires switching, and it's a lot more expensive to test. You tend not to see companies doing mass widespread offline partial discharge testing because it's not viable economically. Some do, normally on smaller networks, but once you start to be a network operator with thousands of cables, it's just not viable. So that's where online testing really starts to pull ahead. So what we have companies doing is some who don't have a good benchmark of their cables, who weren't doing the offline PD testing during commissioning, are now starting to do online testing to gain that benchmark. It's not perfect, you're missing a number of years of data, but they're gaining that starting point. From there, you continue it on a regular basis and you can start to trend your entire fleet of cables. As I talked about, our cable networks are starting to age. On the right-hand side, you can see a bit of a picture which notes the distribution of the age of cables across an Australian DNO. And you can see that most of our cables for this particular network are between 0 and 15 years old, so they're still relatively young. But as this does progress, they want to make sure you've got that really accurate benchmark of data now. So once you do get into the 20, 30, 40-year-old mark for your HV cables, you have the data that you can start to trend and you can make informed decisions. What this has also done to do is doing your wide sweeps is a way of identifying your at-risk cable sections. As you saw in the initial case study I went through, if you test 200 odd cables, the large majority will sit in what would be considered green or low risk. You can then look at what is medium risk and high risk and allocate them to be more of your high risk cables. You need to have some sort of data driving that in order to make your decisions. And I'll talk a little bit about that more in a second. But once you do identify your cables, what is your high risk, what is the most important to your network, you can start to actually look for targeted testing. Now, targeted testing can be rather than doing yearly testing on the cables, you might do 6 monthly, you might do 3 monthly, you might really ramp it up. And it's all about what is viable economically in relationship to what that cable means to your network. A lot of people do this when they find an issue, but they can't quite book the outage. They may have 6 or 8 months until they can do the outage, get the spares, do the replacement. So they will start to do targeted testing in order to trend a known source that they have to make sure that it's not starting to snowball out of control. And that gives you a lot more power as the asset manager to know where it is at every point in time. If you want to go even further, that's when you start to install permanent monitoring. And normally that's for your very critical cables that you are quite worried about, or you know will have a big impact on your network if they are taken offline unexpectedly. So how does that actually work in the real world? And this is a case study out of the UK, where over 2 years, they online tested 191 cables. And what they found is out of those, 17 were in the high category, 14 were in the amp category, and another 160 odd were in the green category, considered fine. So they purposefully did no maintenance on these cables. They left them to see what the results were. And after 2 years, 7 that were in the red category had failed. 3 that were in the amber category had failed, and 3 in the green category had failed. So if you're an asset manager, you're doing this level of sweep, it's really showing you where you need to be focusing your time and energy, because such a small percentage of the green are failing, which is exactly what you'd expect. But a significantly higher percent, 41%, that were designated as the red category led to failure within 2 years. And that's where you need to be focusing your time. Targeted testing is when you're looking at much more critical. So this is a case study for a small industrial site where they had failure on this set of cables, particularly previously. So they decided that during a shutdown, they would install permanent cable monitoring onto it. They re-energized, and 10 days after, they found that one of the cables was starting to trend up in amplitude. They were able to do the waveform analysis, and they found it was all the sources were located down to 308 meters away, which was with a known joint. So with that information, they kept an eye on it. They saw if it continued to trend up, but it leveled out. So they planned an outage, they got everything in place, but in the time between finding that initial source and the outage, they actually noticed that another 2 joints began to show signals of PD beginning to propagate throughout them. These other 2 also corresponded with joints. The probably annoying factor of this is all 3 of those joints were only just installed during the previous outage, so they were brand new. They decided to take all of them out, redo them, and forensically analyze them, and this is what you could do with them. And this is what they found. All 3 separate defects on all of the joints. And it was a really good win for them, because if they lost any of those cables, they stopped production on site effectively. They had not too much redundancy. But it just shows how quickly you could react. It gave them the data and the information they need to book in another outage. And it also gave them reassurance that it wasn't snowballing out of control in the time that they were waiting to get the outage organised. And that, as an asset owner, puts your mind at peace a little bit. So a bit of the summary of all different test methods is the greatest factor about online testing in comparison to offline testing is it's completely non-intrusive. And it shows the cable condition on your real network operations. You're not simulating the network, it is what is occurring. If you take that to the level of monitoring, you can even see it across different loading, different environmental conditions, and you can see a full scope of your network. Due to this, it turns out it's a very quick and inexpensive test, and it can be used to cover not just your cables, but your terminations as well. one thing that becomes really quite prevalent with both online testing as well as, to a degree, the LIRA testing Brad talked about is once you reach transmission level voltages, and it becomes quite difficult to perform offline testing on HV cables that are over 100 kV. It's not impossible, but the test equipment required to do it is a lot more expensive and it's a lot more difficult to actually get to your site. So the difference with both the LIRA test and the online testing is the one bit of kit can test any voltage cable or HV cable. And that is actually quite powerful, and it makes the testing process far easier in the long run. So as I mentioned earlier, we're just going to do a little bit of a small segment on what do we do with this data. You're going out and you're doing condition monitoring tests on commissioning, you're getting that benchmark, you're following that up with a good condition monitoring program. But what are you actually using this data for, and how do you tangibly take that data and put it into a condition monitoring and an asset management program that you can use to make really good decisions about your network? And what we do at EA Technology is we use the CNAIM methodology and the CBRM models. The CNAIM methodology was actually developed by EA, or with EA in conjunction for a lot of the network operators across the UK. And it's effectively a way of rationalizing and bringing all of this data together to give you an asset health index and a risk. And really, this is what a lot of asset owners and asset managers do. If I ever go to a site and I ask them what cables they're worried about, they'll go through and say, oh, well, this particular cable had quite poor readings, we've had failures on it, we've had to put a number of joints in it, and they go through all of the condition tests and you combine them to become one answer. This is what the CNAIM methodology is all about, but it's about standardizing that process, and it's about making it tangible and repeatable, because as asset owners, we're quite good doing one or two cables in your head. But if you have 10, 20, 30, hundreds or thousands of cables, that becomes a lot more difficult process to manage. So you need something that will help you out and make it all, so you're comparing apples with apples effectively. The CBRM models can take that a little bit further, and you start to incorporate not just condition about the asset itself, but also all of the network configuration and the network data that feeds into that asset. And that's when you start to look at performance and risk, and you get a lot better numbers out. So this is just a quick example of what you can do. So this is from a DNO in Australia, but it's a distribution of the health index, so the health of each of their assets across an entire cable network. And as we would expect to see, most of the cables are in the green category. There are a couple in the amber and a lot less in the red, and that's what we'd all expect to see on a network. But the true power of these models is you're not just looking now, because as I said, as asset engineers, we're pretty good at knowing the quality of our cables and their health. But what becomes a lot harder is when you want to look into the future. So the graph on the bottom left is actually, what if we took all these cables as they are now, we did no maintenance, we didn't do anything on them, and we trended them into the future? What are we looking at? And what are we likely to be sitting with in 10 years? And that's when you can take this and you can really start to plan your asset strategies. And you can actually work that into the models to say, all right, if we're doing this, this, and this, so much per year, what will we end up with? But you have to be really careful you don't just focus on the asset itself, because the singular cable itself isn't the whole story. And that's where the CBRM working in the network risk really comes to play out, because the asset health isn't the only factor when it comes to if you need to focus on it. If you've got a cable that has terrible condition monitoring tests and everything, but it feeds a portion of your network that is non-critical, the CBRM models will pull the risk of that cable down compared to a cable that may have medium or good asset health, but feeds really critical portions. And it's by combining both the network as well as the asset health together that you can get some really helpful data that will help you manage your network in the long term. And This is what we're going to be really focusing on during our next webinar. How you go down this process, what are the outputs, how you can use the data to do the full risk calculations, as well as the residual life and end of life of your HV cables. And we're going to go through a case study where what we did is we went start to finish. We did all of the offline testing. We've done the online testing. We've gathered all of the data and built these models for a company, as well as what outputs and how they're using them in the long term. So I really hope you can join us for that one in August, because it should be a really good webinar. The link for that is now open, and you will get sent through the registration for that after the webinar goes through. Thank you everyone for your time today. It's been a really good webinar. If there is anything you need from us, please feel free to reach out. Both Brad and Maya's LinkedIn is there, and we're happy to answer any questions, and we'll try to get back to any unanswered questions that we haven't got to as of yet. Thank you very much for your time. Enjoy the rest of your day.
Goodbye.